Dark energy is the universe deleting itself. The paradox you weren't supposed to notice. You've heard that dark energy is pushing space apart. What if it isn't pushing at all, it's deleting? The universe could be freeing memory by erasing low-value connections, so distant regions stop existing for us because there's nothing left to reference. The strange part, the data has been hinting at this since the late 1990s supernovae. I'll show you what deletion looks like in physics, why acceleration fits a compute limit, what gets erased and when, and how we might catch it mid-swipe. If that's right, the future sky goes black on purpose. Let's confront the problem we pretend is solved. The problem we can't name without lying. Okay, so basically, dark energy is a label for a consequence, not a cause. We measured distant type Ia supernovae in the late 1990s that were dimmer than they should have been in a decelerating universe. Dimmer meant farther than expected, which implied the expansion is accelerating. We patched Einstein's equations with a cosmological constant, lambda, and the math behaved. Our intuition didn't. The simple story says space is speeding up. The honest story says we don't know what's doing that, or whether expanding space is even the right picture. Here's what we actually saw. Two teams, the Supernova Cosmology Project and the High-Z Supernova Search, built Hubble diagrams out to redshifts around Z.5 and beyond. Those standard candles look too faint for a universe whose expansion is slowing under gravity alone. Interpreting within general relativity, you get an energy component with negative pressure, consistent with vacuum energy, driving acceleration. That framework, lambdictum, nails a lot of data. Supernovae, baryon acoustic oscillations, the CMB's acoustic peaks. But then you crash into the cosmological constant problem. Think of it like this. Quantum fields fluctuate even in their ground state. Those zero-point fluctuations contribute a vacuum energy density. When you estimate it using naive cutoffs, you overshoot the observed value by roughly 60 to 120 orders of magnitude, depending on assumptions. That's the worst theoretical prediction cliché, and it lands because it's not a small mismatch, it's an absurdity. Our best quantum calculations say the vacuum should curl spacetime so violently the universe would have torn itself apart instantly. It didn't. So either our calculation is missing a symmetry or subtraction, lambda isn't vacuum energy, or the whole framing is off. Then there's the coincidence problem. Matter density dilutes as the universe expands. A true cosmological constant does not. Yet today their energy densities are of the same order of magnitude. Why now, of all cosmic times, do we live when lambda and matter compete? You can shrug and say selection effect, but it feels like a threshold story we don't understand. Here's what most people miss. We talk about acceleration like a push, but our instruments see subtraction. Signals redshift, interactions weaken, correlation networks thin. In other words, the universe's graph of who can influence whom is losing edges faster than nodes. Cosmology formalizes this as comoving distances growing, event horizons forming, and photons sliding out of useful energy bands. That's not a shove, that's a reduction in connectivity. Everything clicked when I started treating spacetime as bookkeeping. If spacetime is a record of relationships, who can send signals to whom and in what order, then the metric is the format of that record. The speed of light is the maximum reliable update rate. Entropy counts microconfigurations consistent with the record. Holography says information capacity scales with area, not volume, which is a strict budget. In that frame, acceleration could be the system pruning low value, low return links to stay within capacity. Wait, does that imply a simulation? Not necessarily. Digital physics is a stance, not a server room. It says, treat reality as information updated by rules. You don't need a programmer, you need constraints. Planck length and time look like minimum addressable units, resolution and frame rate. Horizons act like boundaries that cap information rate and store summaries on their surface. If the universe runs on a budget, it won't waste compute on maintaining correlations that can't close a causal loop. Here's the counterintuitive part. In fluid language, lambda is a constant energy density with negative pressure. In bookkeeping language, it's an effective background compute tax, steady overhead per patch of area. Early on, when the cosmos was dense and chaotic, long-distance links carried value for future structure. Paying to keep them coherent made sense. As structure growth slows and cross-causality thins, the cost outweighs the benefit. The cheap move is to let far, weakly referenced regions drift beyond causal reach faster. From the inside, that looks like acceleration. If that's the core issue, our language hides it. We say dark energy causes expansion. What this actually means is, the metric update deprioritizes maintaining causal connections beyond a threshold. Geometry reflects that policy. Lambda becomes a placeholder that fits curves while we ignore the budget that might motivate it. Where does that leave us? With a two-part puzzle. First, why does any acceleration exist if naive vacuum energy is catastrophically wrong? Second, why do the symptoms look like connectivity loss, redshift, horizon growth, thinning correlations, instead of a physical push? If spacetime is bookkeeping, a deletion story makes those puzzles rhyme. A finite information budget plus a rational pruning rule produces exactly the observations we brand as dark energy. Remember this detail. It's going to matter later. Horizons summarize. Black hole horizons store information proportional to area. De Sitter horizons carry a temperature and an entropy tied to their surface. If any cleanup happens, it starts at boundaries where signals can't return in time to change the interior. That's the open loop we'll close when we talk about how, exactly, pruning would run without breaking local physics, and how we might catch it in the act. Space as bookkeeping, the digital physics angle. Okay, so basically, stop thinking of space as rubber and start thinking of it as a ledger. Spacetime isn't stuff, it's a record of relationships. Who can send a signal to whom, and in what order? In that view, the metric is just the file format of the record. Change the record and geometry updates. The speed of light, see, isn't a cosmic speed limit so much as a maximum reliable update rate across the network. Try to outrun it and the ledger can't confirm the relationship consistently. No shared state, no causality. In other words, causality is quality control. Think of distance as index gap, not meters between beads. Two regions are far if messages require many hops through weak links. That's why redshift matters. As signals take longer paths and lose energy, the ledger is telling you those links are expensive to maintain. Time then is just the ordering of writes, the commit sequence of the universe's updates. Here's what most people miss. Nature advertises granularity. The Planck length and Planck time behave like minimum addressable units, resolution and frame rate. Below that, our usual notions smear into noise. Stack updates faster than that clock and the record doesn't stabilize. That's exactly how a budgeted information system behaves. Everything clicked when you add holography. We've learned through Bekenstein-Hawking entropy, the generalized second law and holographic dualities, that the information capacity of a region scales with its boundary area, not its volume. That's a storage policy. If reality were bulk stuff, that's weird. If reality is bookkeeping, it's natural. Store summaries on the surface, reconstruct interiors on demand. Think video compression. Edges carry the index. The interior is decoded as needed. Okay, but what actually carries the summaries? Horizons. Black hole horizons have entropy proportional to area and a temperature set by surface gravity. Cosmological de Sitter horizons do the same with the Gibbons-Hawking temperature. Heat here isn't mystical. It's the cost of keeping boundary summaries consistent with quantum rules. You pay in thermodynamic currency to enforce accounting constraints. So what does gravity look like in a ledger? Curvature is the cheapest way to encode relational constraints. If nearby clocks and rulers must agree on causal order, the ledger bends the bookkeeping grid so geodesics reflect that constraint. No forces hidden in the walls, just a minimal description that keeps the record coherent. That's why general relativity loves boundary data. Give it stress energy and boundary conditions, and the interior solution falls out. Now bring dark energy into this frame. The simple version is a background compute tax, a steady overhead per patch of area to keep the ledger coherent. Early in the universe, hot, dense, violent, long links had high return. Structure formation, radiation coupling, mergers, lots of correlation churn. Paying the tax to maintain distant cross-references made sense. As the cosmos thins and cools, cross-causality density drops. The tax doesn't shrink, the value does. A rational ledger prunes weakly referenced edges first. From inside, that looks like acceleration. Think garbage collection. In computer science, objects with only weak references are prime for reclamation. Translate that. Distant, low-interaction regions approach the horizon with dwindling mutual information. The ledger projects what matters onto the boundary and dereferences bulk links. The geometry updates so those regions recede faster in proper distance, not because something pushes, but because the system stops subsidizing their correlation. Here's the counterintuitive part. A constant lambda in fluid language means negative pressure. In bookkeeping language, it means cheaper to expand than to compress. When expansion reduces the number of expensive long-range references per unit budget. Increase area, pay the per area overhead, and in return you cut more costly cross-links than you added. Net win for the ledger, net acceleration for us. Does this wreck local physics? No. A good collector is conservative and incremental. It never frees reachable memory. Likewise, the ledger preserves invariance inside your causal patch. Lorentz symmetry, quantum field theory, local conservation. Pruning occurs at horizons, the safe zones where no signal can return to bite the interior. That's why you don't find anisotropic acceleration in your lab, no preferred frame, no microcausality violations. The policy lives in boundary conditions. The Lagrangian on your bench stays the same. Everything clicks harder with a quick micro story. I tried explaining blockchains to my mom. Distributed ledger glazed her eyes. Neighborhood notebooks everyone compares before trusting a story. She got it. Now upgrade the metaphor. The universe is the notebook. C is the rate you can compare pages. Planck units are the smallest lines you can write. Horizons are the neighborhood fences where summaries get posted. And entropy is how many consistent stories fit on a fence. If a page is rarely read and nobody can bring it back over the fence in time, the neighborhood stops copying it. That's deletion. Finally, notice the pattern across independent clues. C as an update limit, Planck scales as resolution, holographic area laws as storage caps, horizon temperatures as maintenance costs. They rhyme with budgeted computation. You don't have to believe in an external simulator. Digital physics is a stance. Treat reality as information, evolved by rules under constraints. In that stance, expanding space becomes the ledger changing its indexing to cut low-return correlations. The next step is obvious. If pruning is real, it should run at horizons first. So how does the ledger actually write things off without leaving fingerprints? That's where acceleration turns into garbage collection, and where we set traps to catch it in the act. Acceleration as garbage collection. Okay, so basically, if spacetime is a ledger with a finite budget, then cosmic acceleration is what garbage collection looks like from inside the code. In computing, you don't delete hot, central objects. You reclaim memory from things that aren't meaningfully referenced anymore. Translate that to cosmology. Long baseline relationships with low interaction become weak references, and the metric update stops paying to keep them coherent. From our side, that reads as recession speeds increasing with distance, the Hubble law bending upward. Here's the weird part. A true cosmological constant behaves like a constant energy density with negative pressure. That sounds like a fluid that pushes. In bookkeeping, it's simpler. A fixed background compute tax per unit area of horizon. Early on, the universe was noisy, mergers, starbursts, radiation coupling, so long links bought you future change. Paying the tax to preserve those links was worth it. As structure formation stalls and cross-causality thins, the return drops. The efficient move is to prune the quiet edges. The geometry that minimizes cost is the one where far world lines lose causal overlap faster. No hand pushing, just a context shift where near enough to justify maintenance tightens. What does pruning look like in equations? In general relativity, you never see a cosmic janitor flipping pointers. You see the scale factor's second derivative go positive. Geodesics diverge faster, comoving distances stretch, and the proper distance to the event horizon stabilizes to a de Sitter radius. That's the minimal change geometry when you relax long-range constraints in the boundary data. The interior Lagrangian doesn't get new terms, the solution does. In other words, acceleration is a global boundary choice that leaves local physics untouched. Here's what most people miss. Good collectors don't sweep everywhere at once. They work where reclamation frees the most memory with the least disruption. In our case, horizons are perfect. Signals launched from there can't return in time to affect the interior. So if you're going to dereference safely, you start just beyond the horizon. From inside, this is neat. The place where recession naturally exceeds C is exactly where pruning leaves no causality scars. That's not an extra force, it's the algorithm's safe zone. Make it concrete. Take two superclusters billions of light-years apart. Inside each, gravity and feedback still stir, lots of reference churn between them. A trickle of photons that redshift into the noise and very long-wavelength gravitational tides that average out. Those are weak references. As the scale factor grows, the mutual information rate drops below the ledger's verification threshold. The boundary stores what matters, low-rank summaries, and the interior stops funding a live crosslink. The clusters don't feel a push. They just stop coordinating enough state to count as near in the relational sense. The counterintuitive bit is pressure. In fluid language, negative pressure accelerates expansion. In bookkeeping language, expansion reduces the number of expensive cross-references per unit compute faster than it increases the per area overhead. If expanding cuts more maintenance cost than it adds in boundary tax, the cheapest direction is outward. That's why a constant lambda yields acceleration without inventing new particles. It's the sign of a policy, not the shove of a fluid. Does this break local invariance? No. Like a conservative incremental collector, the universe never frees reachable memory. Anything inside a causal diamond remains coherent. Lorentz symmetry, microcausality, and energy momentum conservation, in the covariant sense, stay intact. The pruning only touches links that can't be resurrected, those that would require a round trip through the horizon. That's why you don't see anisotropy, preferred frames, or lab-scale anomalies. The policy lives in boundary conditions. Your benchtop Hamiltonian never notices. Everything clicked for me when I thought about generational collection. Hot, chatty objects get checked often. Cold, quiet ones get swept lazily. Bound structures, galaxies, clusters, are the old generation survivors, compacted into local caches. The vast voids are new generation that get collected aggressively. Observationally, that predicts a subtle, consistent fact. Emptier regions should show sharper effective expansion in comoving terms, and their redshift space distortions should skew toward outflow more than naive lambdictum plus feedback sometimes expects. If deletion prefers quiet edges, voids are where you see the algorithm breathe. Okay, but where's the knob? Budgets pick priorities. The trigger is when the expected update demand from a link, how much future change it supports, falls below the cost to maintain it before the horizon severs return paths. Past that line, the ledger projects to the boundary and drops bulk references. In GR, that's just the comoving separation increasing faster than any signal can compensate. In our language, the reference goes weak, then collectible. Here's a quick micro story. I once built a simulation that lagged unpredictably. Average CPU looked fine. Only the emptiest scenes, big skies, sparse objects caused stutters. The profiler showed GC spikes precisely when the engine could free huge swaths with minimal artifact. Not a bug, a policy. Cosmology feels similar. The most quiescent, largest scale canvases are where acceleration spikes, not because something pushes harder there, but because that's where the ledger saves most by letting go. One last guardrail. A collector that compacts survivors improves locality. Cosmologically, acceleration quietly increases isolation of bound structures, making local physics cleaner over time while starving the global backbone. That's the paradox. The universe gets easier to predict nearby as it becomes less connected far away. If that's how garbage collection shows up in geometry, the next step is obvious. Look to horizons, the boundary caches, to see where and how the ledger writes the write-off. Horizons, firewalls, and where reality goes to die. Okay, so this is where the ledger shows its teeth. Horizons aren't faraway places. They're boundary caches where the record is stored and reconciled. In general relativity, an event horizon is the surface past which signals can't ever return to influence you. In bookkeeping terms, it's the perfect cutoff. Summarize what matters on the boundary and stop paying to maintain bulk details that will never round-trip back inside. From our side, we call that regions receding superluminally. From the ledger's side, it's cleanup with receipts. Start with black holes, the training ground for horizon logic. A black hole's entropy scales with the area of its event horizon, not its volume. That one fact screams storage policy. Information lives on the boundary. Hawking radiation gives horizons a temperature set by surface gravity. That heat isn't mysticism. It's the operational cost of keeping the boundary summary consistent with quantum rules. Unitarity, no cloning, causal ordering. The Bekenstein-Hawking formula is just the invoice for maintaining that consistency. Here's what most people miss. Black hole complementarity says no single observer sees a contradiction. The infaller experiences smooth passage. The exterior observer sees information smeared across the horizon and re-emitted. Two ledgers, both internally consistent. Then the firewall paradox raised a brutal accounting question. Can you keep late-time Hawking quanta entangled with early emissions and still let the infaller see a vacuum at the horizon? Demanding both appears to overconstrain entanglement. One proposed resolution allows a firewall, not literal flames, but a hard cut in correlations at the boundary to protect global consistency. Whether firewalls exist physically is unsettled, but the message is clear. Horizons are aggressive auditors. If the ledger must choose between preserving global unitarity and coddling an infaller's expectations, it defends the global record. Now scale that logic to cosmology. Observations suggest our universe is cruising toward a de Sitter, like phase, effectively constant acceleration, with a cosmic event horizon. De Sitter horizons also carry a temperature, the Gibbons-Hawking temperature, and an entropy proportional to area. Translation: the future boundary has finite capacity and a non-zero maintenance cost. If pruning prefers safe zones where return is impossible, a de Sitter horizon is the cosmic version of a black hole's cache. The ledger projects interior summaries to that surface and dereferences bulk correlations that can't be verified within any interior causal diamond. Everything clicks when you watch horizon geometry in a lambda-dominated universe. As acceleration takes over, the proper distance to the event horizon approaches the de Sitter radius. The boundary's area, and thus its information capacity, stabilizes, even as comoving regions beyond it are effectively written off for any interior observer. From the inside, we say space expands and distant galaxies fade into microwaves, then radio, then practical silence. From the ledger's view, those edges have been summarized and retired. The live link is gone, the receipt is on the surface. Okay, but what would a firewall mean cosmologically? Don't picture a wall of particles. Think of a policy boundary that refuses to uphold long-distance entanglement once the return path is impossible for any observer to consolidate. That refusal shows up as horizon temperature, thermodynamic bookkeeping for enforcing cuts. If a hypothetical super-baseline entangled state spans near the horizon, the ledger won't vouch for joint outcomes that no observer could ever cross-check in a shared future. The practical effect is extra decoherence in absurdly long baseline correlations as you approach the horizon fraction. It's not a local kick. It's a boundary condition that trims unserviceable relationships. Here's the counterintuitive part. The Unruh effect. The heat an accelerating observer perceives fits this logic. Change your relation to a horizon, and the bookkeeping cost rephrases itself as temperature. Different observers slice the ledger differently. The heat is the price each pays to keep their slice consistent. No conspiracies, just accounting expressed as thermodynamics. Let me anchor it with a micro story. A friend asked, does the sky go away? Not physically. The references do. When a galaxy slides beyond your future horizon, photons it emits now never reach you. The ledger does the responsible thing. It writes the galaxy's influence into horizon microstates, coarse-grained summaries that preserve constraints, and stops funding a live crosslink in your interior. To you, it reddens and fades. To the ledger, a line item is closed. Does any of this break local physics? No. Boundary policies change global solutions, not local rules. Lorentz invariance holds in your patch. Fields propagate as usual. Energy momentum is conserved in the covariant sense. The work of acceleration shows up in curvature and boundary thermodynamics, not as a lab-scale anomaly. Horizons are where the engine pays its bills. So where does reality go to die? It doesn't. It gets archived at the boundary. The live web thins as the ledger declines to carry forward correlations that can't close the loop. That's deletion in practice. Project to the surface, enforce consistency, dereference the bulk. If that's the policy, we can ask a sharp question next. What flips a link from live to collectible? In a budgeted universe, there must be a threshold, set by redshifted information rate, interaction sparsity, and horizon approach, where the ledger stops subsidizing long-distance ties. Find that threshold and we can predict when and where pruning sharpens, then design tests to catch it mid-sweep. The threshold. When does the universe start deleting? Here's what most people miss about the why now problem. It smells less like coincidence and more like a crossing. In a budgeted ledger, pruning doesn't start on a date. It starts when a ratio flips sign. So what ratio? Okay, so basically, it's signal to relation density, the usable information rate flowing between regions divided by the number of links worth maintaining. When that drops below a threshold, the ledger stops subsidizing those links. The simple version: when far connections stop paying for themselves before a horizon can close the loop, they become collectible. What drives the fall? Redshift is the quiet killer. Photons stretch, their energies drop, arrival rates smear. The longer the baseline, the more those pings turn into whispers. Stack that with geometric dimming, flux falling as 1 over distance squared, and you get a brutal compounding. Fewer bits per photon, fewer photons per unit time, and more noise competing with the message. Add interaction sparsity. As the universe matures, big-ticket correlations are born slower. Structure growth slows, voids empty, feedback quiets. The reference churn that once justified long links fades. Everything clicks when you marry that to horizons. A future event horizon means there's an upper bound on round-trip verification. If a message can't get there and back inside anyone's causal diamond, then no observer can consolidate a joint state. That matters because the ledger only vouches for correlations that some observer could, in principle, confirm. When the redshifted information rate and interaction yield are so low that verification can't beat the horizon clock, the link's reference count drops to weak. Next sweep, it's eligible. This might seem backwards, but a quieter cosmos erases faster, not slower. If the benefit of a long link is how much future change it enables, then a low-activity era fails the ROI test. Negative pressure in lambda language is cheaper to expand than to compress. In ledger language, it's cheaper to increase indexing distance and cut expensive crosslinks than to preserve them, especially once growth stalls. The metric leans into the cheap direction. We don't pretend there's a magic number published in a paper, but we can name the ingredients of the threshold in ordinary words. Redshifted bit rate. At high redshift, each arriving photon carries fewer effective bits once you price in energy loss and detector noise. Interaction sparsity. Low-density environments and stalled structure growth produce fewer new, high-value correlations per unit volume. Horizon proximity. The fraction of a pair's shared future light cone determines whether any observer can consolidate joint outcomes. Bundle those, and the rule reads: prune when the expected, horizon-bounded mutual information per unit time from a link falls below the boundary maintenance cost it imposes. Here, S-where geometry speaks the same language. In GR terms, this threshold appears when a comoving separation increases faster than any signal can compensate, so local peculiar motions can't restore causal overlap. Past that, the event horizon does the rest. In bookkeeping terms, the link can't be reconciled within budget and time. Same outcome, different frames. Concrete mental model time. Take two big volumes a gigaparsec apart today. Track the weighted mutual information they exchange, photons, lensing, tidal signals, discounted by how much that information can still alter either interior before the horizon forbids a round trip. Early on, that weighted measure is well above zero. As redshift saps energy and the cosmos quiets, it decays. When it crosses a critical fraction, call it the budget line, the ledger marks those edges collectible. The next cleanup cycle, the boundary absorbs the summary. The interior stops carrying the live link. What you infer as acceleration is the geometry reflecting that scheduling decision. The counterintuitive part is that this reframes why now as a phase change. Matter thins, the effective vacuum pressure, our background compute tax doesn't. The crossover happens when the cost-benefit of long links changes sign. Before it, distance spreads seeds. Long links help structure form, so they're worth keeping. After it, distance mostly preserves emptiness, so long links bleed the ledger. Lambda and matter densities being comparable today isn't suspicious in this story. It's the signature of the sign flip. Does this leave footprints we can chase? Subtle ones. You'd expect acceleration's effective strength to ramp as large-scale structures' growth rate declines, consistent with the late-time integrated sacks, Wolf effect being most visible on the largest angles. You'd expect voids, the quietest cells, to show exaggerated comoving outflows and Alcott, Paksinski anisotropies because they cross the threshold earliest. You'd also expect a survivorship bias at high redshift. Sources embedded in dense, self-referential environments stick around observationally longer than isolated peers, after you control for lensing and selection. Not because photons prefer neighborhoods, but because the ledger keeps funding crosslinks that many local records depend on. One more guardrail: local physics stays clean. The threshold is global and horizon-tied. That's why you won't find a local anisotropy in the lab or a preferred frame in atomic clocks. The collector acts only where resurrection is impossible and verification is dead. That's also why any deviation from lambdictum must be scale and epiclimated, living on the widest angles, longest baselines, and latest times. So the threshold answer is boring on purpose. Prune when verification can't beat the clock and the payoff has fallen below cost. That's a rule you can falsify with patient astronomy, which is exactly what we'll do next: turn this policy into risky predictions that could kill it. 5 testable predictions that could kill this idea. Great, nice story. Now let's try to break it. If deletion is real, it should leave small, risky fingerprints on the biggest scales and the quietest places. 5 places to look and 5 clean ways this can fail. Prediction 1. Redshift drift deviates slightly from lambdictum at high redshift. Okay, so basically, if late-time acceleration partly reflects a boundary-driven pruning policy, the long-term change in the redshift of very distant absorbers, the sandage, lobe signal, should show a minuscule tilt relative to a pure cosmological constant history. We're talking Lyman alpha forest systems around redshift Z25, monitored for decades. Lambdictum predicts a specific cm/s per year drift, negative at high z, crossing to positive at low z. The deletion frame predicts the same shape but a hair of extra late time acceleration near the horizon fraction, which slightly shifts the curve. How to test? Ultra-stable spectrographs like ELT-HIRES or ANDES build a 10-20-year baseline. What kills the idea? A time series that hugs lambdictum within stated errors across multiple sightlines, with no coherent excess tilt. Prediction 2. The late-time integrated SACS, Wolf signal is subtly scale-skewed. Here, that's what most people miss. If boundary accounting does work, the largest gravitational potentials decay a little differently than a constant lambda model says. That shows up as correlations between the CMB's large-angle temperature anisotropies and foreground structure. Standard lambdictum predicts a small, positive cross-correlation on large scales. The deletion lens expects any deviation to live only on the widest angles, near the horizon size, and to couple to late-time lensing potentials. Not a big bump, a scale-limited nudge. How to test? Stack high-fidelity CMB maps, Simon's Observatory, CMB S4 with deep surveys, LSSD, Euclid. Include polarization and delens aggressively. What breaks it? A pristine low-L spectrum and CMB. Lensing cross-correlation that fit lambdictum, or simple WCDM, to within tightened errors, with no persistent wide-angle oddities. Prediction 3. Extreme voids expand too fast in comoving terms. If the collector prefers quiet edges, the emptiest region should show a modest excess of outflow and alcock. Paksinski anisotropy relative to best-in-class lambdictum, plus baryonic feedback. Not new forces inside voids, just the global metric solution that minimizes bookkeeping, nudging the largest, cleanest voids across the threshold earliest. How to test? Use Euclid, Roman, and LSSD to catalog thousands of extreme voids, measure shapes, redshift space distortions, and peculiar velocities. Compare to high-resolution N-body plus hydro tuned to galaxy bias and feedback. Pre-register a void boost parameter, an allowed fractional excess in anisotropy outflow for the top percentile by underdensity. What kills it? Observed stacks landing comfortably inside simulation posteriors once systematics are nailed. Prediction 4. A selective high Z luminosity function even after controls. The counterintuitive part. Pruning should produce a survivorship bias where sources embedded in dense, self-referential neighborhoods remain observable longer than equally bright but isolated peers at the same redshift, after controlling for magnification bias and completeness. Translation. A subtle excess of lensed or group-embedded emitters at Z6 compared to baseline expectations. How to test? Assemble environment-tagged luminosity functions with JWST, Roman, and ALMA. Control for lensing, surface brightness selection, and contamination. Compare to forward-modeled mock surveys. What breaks it? Standard astrophysics plus selection pipelines fully reproducing counts and environments, with no residual environment overabundance. Prediction 5. A shared horizon-tied low-frequency noise floor. If de Sitter horizons enforce a finite information rate, observables that sample ultra-low frequencies across vast baselines, pulsar timing arrays, separated atom interferometers, widely spaced optical cavities, might share a tiny, correlated noise floor shaped by the expansion rate and horizon temperature. Not a lab artifact or an astrophysical foreground, a universal hiss. How to test? Cross-correlate PTA datasets with terrestrial and spaceborne interferometers after modeling gravitational wave backgrounds and systematics. Pre-state a target band and amplitude scaling with H and the de Sitter temperature. What kills it? Convergent non-detections and tighter joint limits that leave no horizon-shaped residue. Guardrails to keep us honest. No local violations. Any deviation must vanish on small scales and in local tests. If someone claims a tabletop effect, it's not this. No free parameters after the fact. We pre-register signs, scales, and envelopes, drift curve tilt at Z25, low L cross-correlation envelope, avoid boost window versus radius and redshift, an environment overabundance ratio at high Z, and a narrowband noise amplitude. Miss them, we drop it. Orthogonality. Each line should fail independently. If redshift drift and voids match lambdictum, we don't hide behind quantum links. Multiple nulls end the story. Everything clicked for me when I realized these aren't looking for spectacle, they're looking for policy. Boundary conditions only touch the widest angles, longest baselines, and latest times. So the signals are small, scale-limited, and fussy about systematics. That's good. It keeps us from fitting noise. One more thing, time discipline. The strongest tests mature on decade horizons. So we publish forecasts now, keep analyses blinded, share pipelines, and value replication over drama. If the universe isn't deleting, the cleanest answer is a boring confirmation of lambdictum across all 5 fronts. If even 2 wedge the same way, largest scales, emptiest places, horizon-tide noise, we earn the right to keep going. Bottom line, this idea deserves to risk being wrong. Either future data erase it, or they refuse to, at which point the ledger stops sounding poetic and starts sounding predictive. The engine, how to delete without leaving fingerprints. Okay, so basically, if deletion is real, it has to run at the level of boundary conditions, not bolt weird forces into your lab. The rules you use, Lorentz symmetry, quantum fields, conservation, must stay crisp inside any causal diamond. The trick is global, not local. Adjust the constraints that horizons impose, let Einstein's equations relax to the cheapest geometry, and never touch the Lagrangian on your bench. Here, what most people miss. General relativity is a boundary value problem in disguise. Give it stress energy plus boundary data, and it threads a geometry that satisfies both. So the clean engine is a boundary policy. Horizons enforce an area-limited summary and a finite information rate. When long-range correlations can't be verified before the event horizon forbids a round trip, the policy projects bulk state to boundary microstates and dereferences the interior link. The interior dynamics don't notice, they just propagate on the updated metric. How do you drop data without breaking unitarity? Project then dereference holographically. The boundary encodes a redundant, error-corrected summary. Think quantum error-correcting codes in holography, sufficient to preserve constraints any interior observer could test. Once encoded, bulk degrees of freedom that no observer can collectively access lose independent standing. Information isn't destroyed, it's readdressed at the surface. That's why the heat of horizons matters. Hawking and Gibbons. Hawking temperatures are the thermodynamic price of keeping the summary coherent. Energy bookkeeping is subtle but safe. In covariant form, mu T mu nu equals still holds. There's no local energy pop-in. The work of acceleration lives in curvature and boundary thermodynamics. Vacuum pressure is a shadow of the boundary policy in the global Hamiltonian, not a fluid sloshing in your lab. Inside your patch, know their symmetries still deliver conserved currents. The engine pays its bills at the edge. Everything clicked when I framed the deletion arrow to match thermodynamic time. The policy never rewrites the past. It follows decoherence. Live correlations that can be reconciled within a shared future remain. Those that can't flip to weak, then collectible. That keeps microcausality clean. Operators still commute at space-like separation, and blocks resurrection across horizons. No retrocausality, no signaling, no preferred frame. What about quantum mechanics? Locally, untouched. Fields evolve unitarily on the background you inhabit. What changes is global support for absurdly long baseline entanglement. As a pair's shared future shrinks, the environment that would have maintained phase coherence isn't there. Operationally, the reduced density matrices pick up extra decoherence terms sourced by boundary conditions, not a local bath. To you, it's just a slightly higher noise floor in experiments that stretch light time toward the horizon fraction. Okay, but where's the algorithmic picture? It's conservative incremental garbage collection plus compaction. Mark phase-coherent returnable links, sweep those that fail verification time, compact survivors into tighter locality. Cosmologically bound structures are the compacted cache, the backbone thins. That's why local physics often looks cleaner as cosmic time passes. Fewer long-range cross-dependencies to maintain, more reliable local predictions. The price is isolation. Here's the counterintuitive part. There's no universal horizon that everyone shares in the same way. Each observer has their own cosmic event horizon. Does that make the policy subjective? No, complementarity rescues us. Just like with black holes, no single observer faces contradictions. Each gets a consistent ledger, summaries on their horizon, live links inside. Different ledgers agree where they overlap, and no observer can compare notes across forbidden regions. Global consistency without a God's eye book. What stops the policy from leaking into lab anomalies? 2 guardrails. First, scale separation. Any deviation from lambdictum lives on the largest scales and latest times. Second, symmetry protection. Local Lorentz invariants and gauge symmetries are invariants the boundary must preserve because they're verified constantly inside causal diamonds. If a proposed effect breaks those, it's not this engine. Let's walk a specific path. Imagine 2 regions nearing the event horizon relative to each other. The boundary tracks their mutual information flow, discounted by how much any joint observer could still consolidate. Once the projected reconcilable information falls below the per area maintenance cost, the boundary code locks a summary and flags the bulk link collectible. The global solution relaxes. Geodesics tilt so recession outpaces any compensating signal. The de Sitter radius sets the asymptote. Inside, clocks tick normally. Spectra obey local dispersion. Lab interferometers hum. The only novelty is a gentle, horizon-tied decoherence that you'd only notice across ridiculous baselines. Where do fluctuations sit in this picture? Finite capacity implies an irreducible stochastic floor tied to horizon temperature, tiny, universal, and correlated over huge scales. Miss it, and you call it cosmic variance. Find a consistent, horizon-shaped residue across independent platforms, and you've sniffed policy. Microstory to anchor it. Years ago, I tuned a simulation with brutal stutters. We didn't add cores, we changed the collector. Project old meshes into compressed imposters, free the bulk, compact hot paths. The gameplay got smoother, not because the world grew, but because we stopped pretending we could render everything. Cosmology's engine feels like that. The universe runs smoother nearby because it refuses to render the parts you'll never touch. So the engine's rules are simple. Change only boundary data, project then dereference. Align deletion with decoherence. Preserve local symmetries, never enable resurrection across horizons. Do that, and acceleration shows up as geometry, labs stay boring, and the sky slowly falls off the ledger without leaving fingerprints. Entanglement, causality, and the vanishing web. Okay, so basically, correlations are the scaffolding of reality, not rubber bands in space, shared information. When 2 systems are entangled, your best description of one depends on the other. In the ledger view, that's what existing together means. They share state that can, in principle, be updated in a common future. The richer the shared state, the stronger their joint existence. Why does this matter? Because if the universe prunes to stay on budget, it doesn't erase atoms first. It thins correlations that can't be verified. Entanglement is the highest value correlation we know. Strip it over large distances and the world doesn't break. It fractures into smaller worlds that no longer share enough state to matter to each other. That's what acceleration looks like from the inside. A slow famine of long-range entanglement. Here's the weird part. We know decoherence, entangled states becoming classical when they leak information into a messy environment. There's another route, starvation. If 2 regions can't, even in principle, compare notes in any shared future-like comb, the ledger won't vouch for their joint predictions. The link turns into a weak reference. You can still write down a joint state on paper, but operationally it's empty. No observer can consolidate the outcomes. That's the boundary policy doing its job. Everything clicked when I connected this to horizons. A future event horizon caps who can reunite. As the horizon encroaches, the fraction of shared future between two distant labs shrinks. That fraction is the oxygen that keeps long baseline entanglement meaningful. Starve it, and the reduced density matrices pick up extra horizon source decoherence, not from a local bath, but from the rule that refuses to preserve correlations no one can ever confirm. Let's make it concrete. Think of two galaxy-scale labs trading entangled photons on intercluster baselines. Early on, there's time to reconcile records, send summaries, close loops, check joint statistics. As redshift stretches communication and the horizon creeps between them, those reconciliation paths vanish. Locally, each lab still sees perfect quantum behavior, unitarity, born rule, no surprises. Globally, the observed Bell violation strength across that absurd baseline decays a hair faster than noise and GR alone would predict. Not a dramatic snap, a systematic bias that trends with shrinking shared futures. This might seem backwards because Bell tests don't need communication. Exactly. That's why any horizon-tied distance dependence would be shocking. You're not testing signaling. You're testing whether the ledger keeps endorsing joint predictions that no observer can ever put in one book. If the policy is real, then near-horizon separation should show a tiny, universal shortfall, buried in noise for modest distances, sharpening only as you push baselines toward the cosmic limit. Here's what most people miss. Astronomical Bell tests already weaponize the sky as a randomness source to close freedom of choice loopholes, quasars, stars, even cosmic microwave photons. Extend that mindset. Let distant, mutually space-like sources drive detector settings, while the candidate entangled pairs come from astrophysical cascades. Then, bin events by the fraction of shared future between the detector world lines. If you see any residual trend after annihilating systematics, that's the ledger's fingerprint. If not, great. One more boundary we can't blame. A micro story. Two labs drift apart on a COMC. For years, they flip coins, log results, and later compare ledgers. The correlations sing, they share a world. The tide pulls faster, the rendezvous window closes. They keep flipping, but the day they can never meet again, the only thing that vanishes is the possibility of a joint ledger. Each lab's results still look quantum. The world they once shared no longer exists for them. The accountant didn't smash the coins, it closed the cross-entry. Okay, but what about causality? Safe. Micro-causality, the rule that space-like operators commute, stays intact. No superluminal messages, no retrocausality. The policy is epistemic, not dynamical. It governs which joint predictions remain meaningful when a shared future is gone. In other words, the ledger protects causality by refusing to underwrite correlations that would tempt you to act on impossible cross-checks. There's a practical upshot for civilization-scale experiments. On near-term horizons, we push quantum links stepwise. Ground to satellite, Earth-Moon, Sun, Earth-Lagrange points, then interplanetary. We model every known noise source, loss, timing jitter, gravitational redshift, and watch for a residual that scales with light time and horizon fraction, not with hardware. If every slope lands at zero within errors, deletion lost this round. If not, we've caught policy whispering. The counterintuitive part is what this does to meaning. Meaning is reach. A community that maintains dense, verifiable correlations lives in a larger world. As the cosmic web thins, your patch becomes cleaner locally but poorer globally. The ledger makes your lab easier to predict by starving the long-range backbone. That's comforting and bleak. Your equations get sharper, your universe gets smaller. So entanglement, causality, and the vanishing web aren't side notes. They're the heart of deletion. The universe won't subsidize correlations that can't close the loop. As horizons harden, the far world fades not from malice but from policy. Next, we follow that policy to the end of the timeline and ask what a future looks like when the accountant wins. The black future, a universe that forgets. Okay, so this is the part that lands close. If the ledger runs a budget, the end isn't an explosion, it's amnesia. Heat death sounds like freezing forever. Deletion reframes it. The cosmos keeps only what your patch can still reference. Everything else gets archived at the boundary. Your world doesn't stop. It narrows until every update closes inside your causal diamond. Start with the familiar arc but swap meanings. In lambdictum, acceleration pushes distant galaxies beyond our event horizon over tens of billions of years. Their light redshifts from optical to microwave to radio to practical silence. Stars exhaust fuel. Formation slows as gas gets locked in remnants. Black dwarfs, neutron stars, and black holes take over. Hawking radiation eventually empties the vaults. That's the story you know. In deletion terms, the same beats play as a policy. Galaxies don't just go out of sight, they're crosslinks till you get retired. When a galaxy passes beyond your future horizon, photons it emits now never reach you. The ledger encodes a boundary summary and stops paying to keep a live interior link. You see reddening, dimming, and drift. The ledger sees a closed line item. Nothing dramatic, just a final write to the surface. Here's what most people miss. Isolation isn't mood, it's mechanics. As more of the universe becomes unreachable, fewer long-distance correlations can stabilize your local reality. Bound structures, your merged local group, maybe a beefy elliptical after a long settling, get compacted into a clean cache. The intergalactic medium warms to a floor set by the de Sitter temperature, but you can't touch it. It's a bookkeeping cost, not a usable bath. Your night sky resolves into home field embers, wrapped in an untouchable glow you infer, not feel. Everything clicks when you think of meaning as reach. Meaning is the pattern of influence you can keep verified. Science expanded meaning by widening the web. More baselines, more shared state, bigger diamonds. Acceleration reverses that at the edge, not by smashing atoms but by starving long links of oxygen. The world shrinks while your local laws get sharper. Cleaner near, poorer far. Walk the timeline like a ledger. In the next tens of billions of years, everything not bound to you slips behind the horizon. JWST-class instruments of the far future won't fix that. Horizons aren't detector problems. Star formation peters out as gas settles into remnants. Red dwarfs, the misers, keep flickering for trillions of years, buying time without buying reach. Planetary systems glide in slow choreography. Black holes rule the late stage. The small ones evaporate first, the big ones loiter in the de Sitter bath and then fade. Through it all, the boundary carries receipts, the interior carries less world. The counterintuitive part is that deletion sharpens this isolation. As the de Sitter radius stabilizes, the policy sweep line is ruthless. Anything not nailed to your patch by active, returnable correlations gets archived faster than a naive constant lambda picture suggests, because the ledger optimizes locality. Less action means more pruning. The quieter the cosmos, the cheaper it is to let go. Okay, but what does a day in that long night feel like? Not doom, discipline. An observatory a trillion years from now orbits a cooling remnant. The astronomers, whatever they are, aim absurdly sensitive arrays at a sky that holds only their conglomerate galaxy and a featureless background they can't sample directly. They build exquisite models of local dynamics and tidy myths about a larger past. Every measurement closes inside their patch. Cosmology, as we practice it, collapses into archaeology of survivors. There's a tug in that picture. If existence is correlation density, isolation is entropy masquerading as peace. But there's a sober upside. A good collector compacts survivors to improve locality. Your descendants inherit a patch with fewer cross-dependencies and cleaner invariants. Precision thrives. Repair counts. Skill compiles to many contexts because local context dominates. The price is an end to grand comparisons. Will the boundary ever return what it took? No. Horizons aren't banks that pay out. They're audits. The Gibbons Hawking temperature is the thermostat on the vault door, not a faucet you can open. Information isn't destroyed. It's readdressed to the surface in a code that no interior observer can decode beyond constraints. That's how unitarity and local sanity coexist. A micro-story to anchor it. I once helped archive a sprawling project. We didn't keep every raw file. We kept hashes, schemas, and reconstruction recipes. If a future reader stayed within the documented queries, the world came back. Ask for a raw facet we didn't preserve, and the archive refused gently. The universe's boundary behaves like that. Constraints and summaries preserved, arbitrary details dereferenced. So what's left to do in a universe that forgets? Two things. First, close loops. Build redundant, verifiable records inside your diamond so your patch stays rich. Second, write for the boundary. Encode processes that compile to constraints, standards, symmetries, methods, so the ledger's summaries keep your pattern alive where possible. You won't talk past a horizon. You can make forgetting expensive. The last sound isn't silence. It's a tiny, horizon-shaped hiss, the irreducible noise of a boundary doing work. You'll never touch it. You'll infer it in correlations across enormous baselines you no longer have. That's the soft click of the vault and the quiet policy of a universe that keeps its books. The hack, buying time from a reluctant universe. Okay, so basically, if the ledger prunes what it can't verify, the only real hack is to become hard to compress. Not by shouting into the void, but by raising correlation density inside our causal diamond and embedding our patterns into things the boundary must preserve. 3 moves. Force references, coordinate observers, and learn to write to the horizon. First, force references the smart way. The universe keeps what many independent ledgers rely on. So we engineer signals that appear in multiple orthogonal channels at once. Photons, neutrinos, gravitational waves, pulsar timing. Not louder, richer. Build high-entropy beacons that produce verifiable coincidences across modalities on predictable schedules. A message that reappears as a cross-channel alignment is costly to compress because deleting any one record breaks checks in others. In ledger language, you're inflating the triangle count in the graph, so weak edges become supported by many paths. Fewer single points of failure, more enforced consistency. Here's what most people miss. Entropy can be structure. A cryptographic-grade pseudo-random sequence keyed to stable celestial clocks, millisecond pulsars, planetary ephemerides. Lets distant observers validate each other's slices without round trips. Publish commitments now, with open seeds tied to long-lived ephemerides, so any future lab can regenerate the sequence and compare. If separate patches each hold parts of the key and keep replaying the protocol, the ledger is pressured to preserve those cross-references because they anchor many independent records. Delete one, and too many constraints fail. That makes pruning expensive. Second, coordinate observers into a living mesh. Lone telescopes are easy to forget. Synchronized networks are harder. The simple version: build a civilization-scale interferometer. Start with a planetary ring of optical clocks, fiber links, and space relays. Ladder to moon and Lagrange points, then to interplanetary baselines. Share hashes of raw data in real time. Cross-calibrate continuously. Lock phases between nodes using relativity-aware clock discipline. You're not chasing one grand message. You're maintaining a self-verifying fabric that any subset can audit. In graph terms, every node participates in many loops. A ledger that prunes one edge induces detectable inconsistencies around several cycles, which the interior will flag. The accountant hears that as cost. The counterintuitive part is that activity isn't the goal, verifiability is. Noise triggers pruning, so the mesh needs hygiene, data standards, open schemas, version pipelines, blinded analyses, and ruthless replication. Publish raw with hashes. Pre-register hypotheses and failure envelopes. Design the network to catch its own errors before the cosmos does. The more we police our ledger, the more the boundary must mirror it to keep local invariance consistent. Third, learn to write to the boundary. Horizons preserve summaries, not stories. So we encode what we care about as constraints, not cargo. 2 tactics. 1. Ride conserved quantities and low angular momentum modes, signals that project cleanly into horizon microstates. Standard candles aren't enough. We want standard processes. Gravitational wave chirps from engineered binaries, clock ensembles that realize symmetries, spectral combs tied to fundamental constants. 2. Live as a protocol. Cultures that encode identity as reproducible procedures, calibration rituals, measurement grammars, error-correcting codes, compile to boundary constraints. If many independent ledgers instantiate the same protocol, the cheapest summary includes it. Places get dereferenced. Protocols persist. Microstory to anchor it. A project I loved survived a storage crash because 3 teams in 3 countries kept independent mirrors for different reasons: teaching, tooling, and curiosity. None set out to be the archive. Together they were. That's the mesh, not a monument, a habit. The ledger deletes singletons, it hesitates to delete triangles. Okay, but how do we avoid perverse effects? More activity triggering faster pruning. Boundary-aware signaling. Don't flood. Target channels the horizon already pays to maintain. Conserve charges, symmetries, long-lived clocks. Use pulsar-timed commitments, multi-messenger standards, and gravitational baselines less vulnerable to dust and dimming. Favor redundancy over volume. The test is simple. If deleting you would create contradictions across independent, slow-changing records, you're sticky. Concrete starter kit. Build a global time mesh anchored to optical clocks and pulsars. Publish weekly, signed ephemeris hashes. Launch interplanetary interferometers that self-calibrate via shared sky and release raw visibilities with open tooling. Seed a gravitational wave metronome by tracking long-period binaries as reference beats. Maintain public, versioned archives with cross-jurisdiction mirroring and Merkle tree commitments so future readers can verify provenance. Teach the protocol, measurement literacy, error budgets, adversarial collaboration, so the method outlives the medium. There's a civic layer too. Institutions that braid independent oversight, journals that require raw, teams that pre-register, funders that reward replication, raise the cost of forgetting entire fields. Pair disciplines that rarely talk and force them to produce joint predictions. Cross-train engineers and astronomers so instruments and questions co-evolve. These aren't vibes, they're correlation engines. Will any of this beat a horizon? No. Horizons aren't negotiable, but you can make forgetting you costly. If the universe keeps what many ledgers rely on, then our survival move is boring and profound. Increase verified, low-noise ties per unit cost and encode ourselves as constraints the boundary must carry. We can't own the distance. We can own the density. Clues in plain sight. Anomalies that nudge the door. Okay, so basically, if the ledger policy is real, its fingerprints should show up exactly where our models are thinnest. The widest angles, the emptiest places, and the latest times. Not proofs, patterns. Correlation isn't causation, but consistent nudges in the right regimes earn a closer look. Start with the cosmic microwave background at the largest scales. The standard picture, lambdictum with a nearly scale-invariant Gaussian primordial spectrum, predicts statistical isotropy. Yet the quadrupole amplitude is low, and some of the lowest multipoles appear oddly aligned, what people nickname the axis of evil. Most experts treat this as either a statistical fluke or residual foregrounds. Fair. But in a boundary-driven story, that's where you'd expect any tiny departure. Modes whose wavelengths approach the horizon size are most sensitive to how the boundary sets global constraints. If future, cleaner maps and foreground models keep a mild, horizon-scale oddity alive, that's a nudge toward policy at the edge. Everything clicked when I looked at the late-time integrated Sachs Wolf effect. As dark energy takes over, gravitational potentials decay, leaving temperature imprints in the CMB that cross-correlate with foreground structure. Lambdictum predicts a small, positive signal on large scales. Measurements find hints, but the amplitude and angular dependence wobble, especially at the grandest angles. if deletion slightly accelerates the decay of the very largest scale potentials. Because the ledger relaxes long links first, you'd see a scale-limited tilt, no drama on degree scales, a whisper near the horizon angle. If upcoming CMB polarization and delensing from Simon's observatory and CMB S4 tighten errors and land squarely on lambdictum, great, policy sits down. If a coherent, wide-angle residue remains, that's a second nudge. Now the Hubble tension. Local distance ladders using Cepheids and Type Ia supernovae yield a higher H than early universe inferences from the CMB under lambdictum. People propose systematics or evolving dark energy. Our frame doesn't claim the tension, but it offers a lens. Late-time, boundary-shaped geometry could bias local inferences without touching recombination physics. If the ledger slightly boosts late-time acceleration in a scale-dependent way, calibrators embedded in certain environments might ride that context. If DAISY, JWST, and standard sirens harmonize H across methods, we lose a flashy talking point. If they don't, if late-time inferences remain high even as systematics shrink, that's a third cautious nudge. Here S where voids talk. The emptiest regions are precisely where a collector would save the most by letting go. Observationally, the largest, cleanest voids sometimes show stronger apparent outflows and Alcock-Paksinski anisotropies than naive expectations, though baryonic feedback and galaxy bias muddy the water. If Euclid, Roman, and LSSD stacks reveal a persistent, modest void boost after careful modeling, especially for the most extreme underdensities, that's consistent with early threshold crossing in quiet cells. If high-fidelity simulations with realistic feedback swallow the discrepancy, deletion doesn't get credit. The giant CMB cold spot sits at the edge of this conversation. One explanation is a line-of-sight supervoid producing an integrated Sachs, Wolf dip. Another is it's a fluke. Our stance doesn't magic it away. It just says, if boundary-first bookkeeping slightly relaxes potentials in the emptiest, largest structures, a supervoid could punch a touch harder than standard modeling would suggest. If better void maps and polarization data folded into lambdictum, good. If a stubborn, environment-linked anomaly survives, that's another nudge. Zoom down a notch to small-scale structure. Missing satellites and too big to fail now look largely explainable by feedback and reionization, but the language echoes granularity, fewer effective degrees of freedom at the faint end. If the ledger naturally de-emphasizes low-impact, weakly interacting detail, especially in correlation-poor environments, you expect observation to prefer smoother summaries. If next-gen surveys close the gap entirely, great. If a resistant tail remains after brutal modeling, it rhymes with compression. Here's what most people miss. These aren't free passes to staple anomalies to a cool story. They live where systematics breed, low LCMB, cross-correlations, void statistics, selection functions. That's exactly why policy could hide there. It looks like the mess we already fight. The right bar is we see something weird. Its independent wedges point the same way. So we ask for three convergences. A persistent, horizon-scale quirk in low LCMB intensity polarization that refuses to die with cleaner foregrounds, with phase and amplitude confined to the widest angles. A void boost, shapes and redshift space distortions for the most underdense, largest voids, sitting just outside best lambdictum plus Barrian prediction bands, consistent across surveys and redshifts. Late-time cross-correlations, CMB lensing with galaxies, ISW stacks, favoring a slightly time and scale-dependent potential decay aligned with boundary cost, not arbitrary equation of state wiggles. Microstory. I once debugged a renderer by profiling average frames, looked fine. Only when I graphed the worst scenes, huge empty vistas, did I catch garbage collector spikes. Not a bug, a policy, free where it's cheap. Cosmology feels similar, averages behave. The widest angles and quietest places sometimes don't. If cleaner data tame every spike, we walk away. If the spikes persist, small, scale-limited, and coherent, the ledger may be peeking through. Caution again. Correlation isn't causation. We lock predictions before data land, prune degrees of freedom, and accept nulls. If redshift drift hugs lambdictum, if low L and lensing settle, if voids match simulations, if high Z environments show no extra bias, if horizon tide noise is absent across platforms, then deletion loses. If multiple, independent nudges stack in the same direction, we keep going carefully. The experiments that could break this. All right, time to stop theorizing and put chips on the table. If deletion is policy, the cleanest confirmations live where boundary conditions actually matter. Decades-long clocks, horizon thermodynamics, the emptiest structures, and quantum links stretched until the shared future vanishes. 5 lines of attack, each with a hard fail condition so we can't wiggle later. First, spectroscopic time drift, the Sandage lobe signal. Stare at the Lyman alpha forest in quasars for decades and watch redshifts creep by centimeters per second per year. Lambdictum makes a sharp prediction. Negative drift at high redshift, around Z approximately 4.5, flipping sign and going positive at low redshift. The deletion stance keeps the shape but whispers a late time tilt, a hair of extra acceleration that lives near the fraction of sky approaching the event horizon. How to do it right? Ultra-stable spectrographs like ELT-HIRES and Andes, laser comb calibration, vacuum-sealed optics, and obsessive systematics. Pre-register the envelope now. Maximum allowed deviation versus redshift over 20 years. What breaks the story? Multiple independent sightlines hugging the lambdictum curve inside that envelope with no coherent tilt. If the drift is textbook, our boundary tweak is gone. Second, horizon fingerprints in CMB polarization and lensing. If boundary accounting trims the very largest scale potentials, it shows up only on the widest angles. Low letter 2113E modes their phase, and the cross-correlation with reconstructed lensing. The standard model expects a small, well-shaped late-time integrated Sachs-Wolf contribution. We expect, at most, a sub% horizon-limited nudge that correlates with late-time lensing potentials after aggressive delensing. How to do it right? Simon's Observatory and CMB-S4 for low-noise polarization, careful galactic foreground cleaning, cross-checks with Planck legacy maps, blinding and null tests baked in. What breaks the story? A pristine low-letter 2113 spectrum in CMB, lensing cross that match lambdictum or simple WCDM within tightened errors, with no persistent wide-angle oddities. If the sky is clean, policy keeps quiet. Third, deep void cartography. Quiet regions are where a collector saves most by letting go. The prediction is modest. The largest, cleanest voids show a small excess in comoving outflow and alcock. Paksinski anisotropy relative to best-in-class lambdictum, plus baryonic feedback. Not new forces inside voids, just the global geometry relaxing long links first. How to do it right? Use Euclid, Roman, and LSSD to assemble an extreme void catalog. Forward model galaxy bias. Include redshift space distortions. Measure peculiar velocities with kinetic Sunyaev-Zeldovich stacks. Pre-register a void boost, parameter versus effective radius and redshift. What breaks the story? Observed stacks landing comfortably inside simulation posteriors after feedback and selection are nailed. If voids behave, pruning has no extra bite. Fourth, ultra-long baseline quantum links. Locally, quantum mechanics stays crisp. The test is global support for absurd separations. The boring, falsifiable prediction. After you model loss, timing jitter, detector darks, and general relativistic redshift, Bell violation strengths and entanglement fidelity decay with light time a hair faster than expected, trending with the shrinking fraction of shared future rather than with hardware. How to do it right? Step ladder baselines, ground to satellite, Earth, Moon, Lagrange point relays, then interplanetary pilots, tight clock discipline, device-independent protocols, measurement settings driven by mutually space-like astronomical sources. What breaks the story? Residual slopes consistent with zero within errors across baselines once GR and noise are modeled. If every dataset lands on standard theory, the boundary source decoherence term doesn't exist. Fifth, horizon rate noise floors. A finite de Sitter information rate should leave an irreducible, correlated hiss at ultra-low frequencies, shared across platforms that sample vast baselines. Pulsar timing arrays, distant atom interferometers, perhaps synchronized optical cavities spread planet-wide. It must be distinct from nanohertz gravitational wave backgrounds and technical noise. How to do it right? Cross-correlate PTA datasets, e.g., nanograv, EPTA, PPTA with terrestrial and spaceborne interferometers. Model out known astrophysical backgrounds. Pre-state a narrowband amplitude that scales with H in the Gibbons, Hawking temperature. What breaks the story? Convergent non-detections and tighter joint limits that leave no horizon-shaped residue. Guardrails keep us honest. No local anomalies. Anything we claim must vanish in lab tests and small-scale structure. No parameter drift after the fact. We publish signs, scales, and envelopes now. The redshift drift tilt at Z approximately 2.5. A low letter 2113 polarization and CMB lensing envelope. The void boost window. A slope limit for excess fidelity decay versus light time. And a noise floor amplitude band. Orthogonality is non-negotiable. Each line can fail independently. If redshift drift lands on lambdictum and voids behave, we don't retreat to quantum links. Multiple clean nulls end the story. Practically, this demands clock-level culture. Blind the analyses. Share raw and pipelines. Publish null tests before headline plots. Replicate across instruments and hemispheres. Reward verification as much as novelty. The boundary policy idea benefits most from being ruled out cleanly. If the universe isn't deleting, a boring confirmation of lambdictum across these fronts is a win for clarity. If even two independent wedges nudge the same way, largest angles, emptiest places, and longest baselines, then horizons as hard accountants moves from metaphor to mechanism. Either way, the data decide. Meaning under deletion. Why this matters to you. Okay, so basically, this isn't just a cute cosmology frame. It's a rule for what stays real in your life. Existence follows updates. The universe keeps relationships it can verify, it archives those it can't. Your brain works the same way. Friendships you keep feeding feel vivid. Skills you practice feel alive. Projects you revisit stay coherent. The rest turns hazy, then feels like it never mattered. Deletion isn't doom. It's the penalty for neglect. Here's what most people miss. Attention isn't a vibe, it's infrastructure. When you pay attention, you're funding a link. You're raising correlation density, more cross-checks, more shared state, fewer surprises. That's why a team that measures, logs, and shares beats a team that talks. That's why open methods trump secret sauce. The ledger doesn't care about promises. It cares about verifiable ties per unit cost. Everything clicked for me when I reframed meaning as reach. The wider your web of reliable updates, the larger the world that's real for you. Science is the master hack here. Standards, replication, distributed sensors, error bars. It turns scattered observations into a shared causal diamond so we can disagree productively inside common constraints. That expands world. By contrast, censorship looks tidy but acts like pruning. It kills cross-checks, collapses variation, and makes compression cheap. You gain narrative, you lose reach. So what does living under deletion actually look like? 3 moves. First, braid channels. Don't trust a single medium. If you care about a result, tie it to independent signals, code, data, procedures, and people who don't share a boss. Publish raw with hashes. Archive in multiple jurisdictions. Write README files like you'll be audited. You're not being paranoid. You're raising the triangle count in your graph so weak edges become supported by many paths. The ledger hesitates to drop triangles. Second, encode protocols, not monuments. Places get dereferenced, procedures persist. A craft you can teach compiles to many contexts. A job title doesn't. Write your identity in calibration rituals, repairable designs, version tools, and method literacy. Show how to measure, not just what you measured. That way, when the medium rots, the pattern reappears wherever conditions recur. You're living as an error-correcting code. Third, structure disagreement. Truth survives when smart opponents can catch and fix each other's mistakes without burning the lab down. That means pre-registered predictions, blinded analyses, adversarial collaboration, and incentives for replication. It's slower up front and faster forever. The ledger likes invariance. A culture that forces joint predictions becomes sticky. Here's a micro story. A colleague once saved a field by losing an argument. Two groups, incompatible claims, months of heat. Instead of doubling down, they co-designed a decisive test, shared pipelines, and pre-registered pass-fail lines. Their conclusion sank one pet idea and birthed 3 better ones. They didn't just keep a fact, they kept a protocol. 10 years later, new teams recompiled the method and found new things. That's survival under deletion. Okay, but doesn't all this just mean work harder? No, work cleaner. Noise triggers pruning. You want fewer, stronger ties, not more shouting. Filter your inputs. Keep long-form baselines with people who will tell you you're wrong. Batch novelty, automate routine. Treat your calendar like a cache. Compact hot paths, free cold ones. You're not optimizing for excitement, you're defending bandwidth. There's a personal cost, and it's worth naming. As horizons encroach, cosmic, cultural, or algorithmic, your default reality shrinks unless you act. The antidote isn't more takes, it's more tests. A slower feed, a deeper bench, and rituals that force you to touch the work. Read full papers, not threads. Build a small instrument and calibrate it. Fix something physical. Teach someone younger the method, not just the result. These are stubborn, boring moves. They're exactly what the ledger rewards. Zoom out to institutions. Universities, journals, and funders either amplify correlation density or fake it. Reward raw data releases, negative results, and cross-team replications. Tie grants to open tooling and do-or-die pre-registration in high-variance subfields. Pair disciplines that rarely talk and demand joint forecasts. Build public testbeds where rival ideas must make next-year predictions. Don't force consensus, force comparable output. And yes, there's a civic layer. A society that values long horizons funds archives, maintains standards, and trains measurement literacy like reading. It builds small world networks with strong bridges, not giant platforms doing algorithmic erasure, not siloed cliques. It keeps speech accountable without compressing dissent into mush. That doesn't mean everyone gets a mic. It means everyone gets a method. The existential slice is simple and sharp. If existence follows updates, then neglect is self-erasure. You can't stop horizons, but you can slow forgetting. Keep triangular ties, encode protocols, track your own error bars. When possible, tie your meaning to conserved structures, symmetries, shared measurements, clocks that will outlast you. That's how patterns outlive mediums. One last micro story. A friend's family lost a language in a generation. 2 grandparents fluent, parents half-competent, kids with a few songs. They resurrected it not with a dictionary, but with a weekly ritual: cook, talk, sing, and record. They built a protocol, then braided channels, audio, text, video, recipes. In 10 years, cousins who never met can now argue about food in a tongue that was gone. That's deletion in reverse, not louder, richer. So why this matters to you? Because the universe won't subsidize relationships that never close the loop, and neither will your life. Close loops. Make forgetting expensive. Live as a protocol. That's how you keep your world big when the sky thins. The one-line takeaway, and what to do next. Dark energy might be bookkeeping, the universe pruning unconfirmable correlations to obey a finite information budget. If you want the practical playbook, how to encode work as boundary-friendly protocols and track those 5 falsifiable tests, subscribe and watch the next episode. We'll set hard prediction envelopes, publish checklists for boundary-aware signaling, and follow the new data as it lands.